4.1 Polynomial functions and models. Okay, so a polynomial function in any given form will just have some coefficient that goes with the variable with some exponent. And then when I finish writing the coefficients, I will write all my variables in descending order. So if this was to the fourth, my next term would be 3, so I would subtract 1 from each of my exponents. Then my next variable and exponent will be 2 less than the original one, unless of course I didn't have it, and then I wouldn't worry about writing it. Okay, and then we usually write it like dot dot dot, and then you have something, your coefficient of your x term, and then plus something which would be your constant term, which we write a to the 0. Okay, and then we have different types of polynomial functions. And so then we'll have some examples of them, and I'm just basically taking this table from the book. So we'll make like a polynomial, we'll make an example, we'll also state the degree, what the leading term is. The leading term when it's written in descending order, so the highest thing comes first and then we write down our powers down. We'll write out all these things, and then we have leading coefficient as well. So the coefficient is a number in front of the variable, and the leading term is that piece with the variable with it. So you have to actually look at what I'm asking you. So the type of polynomial, if we were just to have a constant term, a constant polynomial, can't spell constant, that would just be 3 or like 5, some just random number, it doesn't matter, and all it's going to be is a number. If I were to have, say, 3x to the 0, that's really what this is if I were to consider this even up here. Okay, but we usually don't write that. Anything to the 0 power is just 1, so 3 times 1 is just 3. The degree of anything constant, so anytime I just have a plain old number, is always 0. The leading term will be just whatever it is, and the leading coefficient will also be the same thing. Now for my next example, if I had a linear function, a linear polynomial, and that would give me, so they have f of x equals 2/3 x plus 5. My degree, my power of x right here is 1. And my leading term would be 2/3 x, and my leading coefficient alone would just be 2/3. Then my quadratic is which we've been doing a lot of lately. My leading term and coefficient will be like my ax squared and my just the a of this. My example, so I have some function equals 3x squared plus 2x plus 1. The signs don't matter, it could be negatives. My degree on this guy would be 2, because that's my highest power. And it doesn't even matter, I could also write this the same function as 2x plus 3x squared plus 1. It does not matter the order that I write it in to find my degree. My degree is actually always just whatever the highest exponent is. My leading term, my term would actually be 3x squared, and my leading coefficient is 3. Okay, and I can look at this no matter what power it's written in. And then my next example is a cubic function, a cubic polynomial. So cubic means cubed, so we'll have a 3. So f of x equals x cubed plus 2x squared plus x minus 5. So I don't remember if I was writing a 5 there. My degree for any cubic function will just be a 3. And my leading term in this case will just be x cubed. And my leading coefficient will be how many x cubes I have, and there's just 1. So only think about how many you have. Anytime, basically I describe a cubic as my leading coefficient cannot be 0. Because if I were to happen to have a 0, then it would actually make it a quadratic function. So then I have my next type is a quartic. Quartic, think there's 4 quarts in a gallon, and that will be x to the 4th. So their example that they have is negative x to the 4th. I don't care about the rest of the example. Plus 7. My degree here is 4. My leading term is negative x to the 4th. And my leading coefficient here is actually negative 1. And then let's do some quick graphs on some examples. So an example of a constant function, it would just be a straight line. Or whoops, that's a really bad example. It would be a straight line that actually is flat. So it has a slope of 0. A linear function is going to have a positive or negative slope. A quadratic function, we've done plenty of those lately. So your quadratic functions can either look like that or that. A cubic function will look like that or that. And a quartic can have a few different types of looks. It can look really lumpy. And I'm making really nice graphs, actually, and I'm proud of myself. And actually, some quartics will actually look kind of just like a parabola and have a quadratic kind of look to them when we're asked to look at those graphs. We don't really talk about them being quartics. We usually just will actually have something already given for us that will look like it's actually a quartic. Okay. Some examples of things that are not polynomials would be 2x plus 5. Anytime there's an x in the denominator. So these are things that are not polynomials. Okay, so this is an x in denominator. It doesn't matter if it's an x if there's really anything in the denominator. Anytime the other way that this thing could be written, that you might not see it being in the denominator, it would also be written as 2x to the negative 1 plus 5. This is the same equation. I cannot have any negative exponents. Negative, I'm going to actually spell out negative. So I can't have negative exponents. And also things that are not whole numbers that are positive. So if I had the square root of x plus 6, this is really, I can't have a square root. I didn't spell square right, so hopefully you guys can spell square. And this would be the same thing as having x to the 1/2 plus 6. So those are equivalent things. Okay, and fractiony exponents. And then I'm going to talk about the end behavior on odd and evens. That's not an odd. So I had odd or evens. And we're going to talk about the end behavior. So odd ones. So if the degree is odd, so we have an odd degree. If it's positive, my graph will start down here and it will end up here. So they will go different directions. If it's negative, it will start on this side and it will go down over here. Oops. So it doesn't matter what's in between. So it talks like it kind of has like a squiggle line on it on their graphs when they ask you to look at them. So, and if it's an even degree, they're going to go the same direction. So if it's positive, I will have 2 things going up. And again, I really don't care what happens in here. So that's a happy, crazy, smiley face. If it's negative, they will still both be going the same direction if it's even, and we don't care what happens in here. Okay, so odd degrees, I always remember that they go opposite directions. Opposite and same direction. My pin's not working very well. So when we talk about positive or negative, I am talking about the leading coefficient. So that is just talking about the leading coefficient. So some of the questions kind of ask you to describe the end behavior, and they would have like an A, B, C, and a D on your graphs, and you're kind of basically doing a really simple graph matching kind of thing. So if my graph was, or if my equation was 2x cubed minus 1, which of these is going to best describe, which of these A, B, C, or D is going to best describe how this fits? So 2 is a positive, and 3 is odd. So my best example would be A. So A would be like what my answer would look like for that. Then if I had negative 4x squared plus 2x minus 3, negative 4, so that's negative and it's even. And so my answer would be D. So there's a few of those kind of questions where you're just kind of doing a simple graph matching. Another thing about graphing that we'll do is no matter what my equation is, so I just gave you the equation 2x cubed minus 1, my a to the 0, or a sub 0, is equal to negative 1. And what that is always going to be is my a sub 0 is my y-intercept. And always think of a sub 0 as my constant term. So this is my constant. And that is where it's going to cross the graph. So I just said that my end behavior was going to be down to up. And then if I were to just do my graph real fast, so I have my graphing lines. So a cubic function, so negative 1 is where it's going to cross my x-axis. So we're going to say right here. So I don't even really, I'm not even terribly worried about what's happening in here. I want you guys to be able to find my y-intercept and tell me the end behavior is kind of the most important pieces of the graphing. We'll get to some other pieces. Okay, but that y-intercept is where it goes through. So if I had my next equation, let's say negative x to the 4th plus 2x cubed. Okay, so it is negative and even. So what I know that's going to happen is my end behavior is going to be something like that. And if I really look at this, I don't have anything else happening. I'm not adding or subtracting anything onto this. So really, like if I wanted to write it, I would write plus 0 at the end to find my constant. Since it's not written, it's just 0. I don't have to actually write it, which means it's going to go through this point. So I could have all kinds of crazy quadratic-y or quartic stuff, and it could be like that. It could be just a real quick, just it goes through there, but it would be something through 0, and it would be even ends, so they'd both go down. Okay, what the graph actually looks like is like that. So that's what your actual graph would look like. I want you to be able to find that y-intercept and my end behavior first, though. So if I just had the equation f of x, and most of them will be written as f of x or g of x. So if I have f of x equals negative 5, if my normal graph was this thing, then I will have negative 5. 1, 2, 3, 4, 5. Let's say negative 5 is down here. And so it'll be flat. Okay, and then some of your questions are actually, you're asked to find whether or not some different zeros, are zeros of the function that they gave you. So this one will be whether 1, negative 2, and 3 are zeros. Oh, I can't even spell zeros. Are zeros of, I still can't spell zeros. There's no E in it, although I always want to put an E in it. Are zeros of the equation x to the 4th minus x cubed minus 3x squared plus 5x minus 2, and this is g of x equals this stuff. So what I'm actually going to do is I'm going to write g of 1. And then I will get 1 to the 4th minus 1 cubed minus 3 times 1 squared plus 5 times 1 minus 2. What I'm going to get is 1 minus 1 minus 1 squared times 3 is negative 3 plus 5 minus 2. And when I actually go through and do that, I will get, oops, my thing's not working very well. So these guys will add to 0. So I'll have negative 3 plus 5 will be positive 2 minus 2 is 0. So g of positive 1 equals 0. So this would be a yes. Yes, 1 is. So that's how I would write my answer. So I'll basically have yeses or nos for my answers. Then let's plug in 3. So let's just ignore negative 2 right now. So we'll do g of 3. What I want to get out is 0. And I'll have 3 to the 4th minus 3 cubed minus 3 times 3 squared plus 5 times 3 minus 2. So 3 to the 4th is 81 minus 27 minus another 27 plus 15 minus 2. 27 and 27 is 54. So that's minus 54. So all my negatives, so I like to group all my negatives together and all my positives together. So 81 plus 15 is 96 minus 56. So 54 and then negative 2, and that should be 40. So g of 3 is equal to 40. So my answer then would be no, which is not what I'm going to add to it. So I have a yes and a no, and that's how you'll write some of your answers. Okay, we did a lot of things when we were actually factoring, so you guys should be pretty good at factoring. But I have f of x equals x cubed minus 2x squared minus 9x plus 18. And most of the things that you'll see will factor pretty nicely. I believe you guys are good enough at actually factoring. So I'm going to factor the front and the back. So anytime I can't pull something out of every single thing, I will try to break it down through the middle. So what comes out of these first two terms, and that will just be an x squared. I'll be left over with an x minus 2. Since I want a minus, and these two signs, this is a plus, I need to actually factor out a negative something. So in this case, it'll be negative 9 that I can pull out of both things. And I will be left with x minus 2, because 18 divided by negative 9 is negative 2. Okay, since I have x minus 2 in both places, I pull out the x minus 2, and I'm left with x squared minus 9. Anytime I have an x squared left over, I need to try to factor it more. So this is actually a difference of squares. That's a C. So you'll try to always keep factoring. I'm still left with the x minus 2 out front. And the square root of x squared is x. So if you remember your difference of squares, I have a plus and a minus. The square root of 9 is 3. Okay, so what I'm then going to say is I'm basically solving these things down, and I will be left with x equals 2, x equals negative 3, and x equals positive 3. Now this is basically that next step to graphing, which you're not always going to be asked to graph it, but I want you to realize kind of how it will look like on a graph. Since none of these things repeat, and I will show you what some of them look like when they repeat, I will just say what my roots are, and these all would be considered to have a multiplicity of 1. So the way your book actually wants you to write it would be like 2 multiplicity of 1. And then write a semicolon, negative 3 multiplicity of 1. And we'll talk about multiplicity in a second. And I would have 3 multiplicity of 1. If I were to look at this on a graph, what this would actually mean is I have 3 different times that this thing actually hits the x-axis, and that will happen at 2, 3, and negative 3. But I can also look back at my original equation, at least on these ones that are already, but that I actually have to factor. Some of them you can't look at. And so this will actually go through at positive 18, so that happens somewhere up here on the y-axis. Since I know that it is odd, my end behavior will go like this, since it's also positive. So I basically need to make it through all these marks without going sideways back and forth. So my graph, I'm going to hit this one first, and then I'm going to come up here, and then I'm going to come down, and I have to actually go through my points. And the multiplicities will determine whether or not I go through them or if I just touch those points. Since these all had a multiplicity of 1, I go through those points. So I will show you ones that have a multiplicity of 2 now. Okay, so the next one that I'm going to do is actually number 34 for you guys. And so that problem says f of x equals x squared. And so this one's already factored, so we take down a lot of the work. And then I have x plus 3 squared times x minus 4 times x plus 1 to the 4th. So now what I'm going to say is basically I'm going to treat this like a separate factor. It is a separate factor. But anytime I have that x out front, people tend to forget about it. So when is that first piece going to equal 0? When it is at 0. So I will have 0 with a multiplicity of 2 because of this squared. Anytime I have a squared or any exponent, that's what my multiplicity will be. My next thing will be x equals negative 3, and that will have a multiplicity of 2 as well. My next one is x equals positive 4 with a multiplicity of 1. So even if I have a multiplicity of 1, I still need to state it for polynomials. And then the next piece I have x equals negative 1. And that will have a multiplicity of 4. And you're not really asked to graph it, but if you were asked to graph it, what I would do is I'm going to basically count up all the multiplicities that I have, which will also tell me how many x's I had if I were to actually multiply these out. So this is going to be 2, 4, 8, 9. So this is a polynomial. So this is a 9th degree polynomial is I guess how you would say it. So this is a 9th degree. Not all your questions ask you that. Polynomial. Then what I'm going to do, since I know it's odd, And I don't have any negatives in front of any of my x's, so I also know that it's positive. So when I actually go to graph it again, and none of these graphs are going to look like exactly right, since it's negative, or since it's positive and odd, they're going to go opposite directions, but start down and go up. I'm going to go through 0, and it has a multiplicity of 2. So what that actually means is that it's just going to touch it. It's not actually going to go through it. And then I have a -3 with a multiplicity of 2, and a 4 with a multiplicity of 1, and a -1 with a multiplicity of 4. So my odd ones, I will go through, and I will actually go through them. My even ones, I just barely touch it. So my first one that I go through is -3, and it has a multiplicity of 2. So I just go up and touch it. I don't actually go through the point. My next one is -1. Since it's even, I just go touch it. We're not really overly concerned with what happens in the middle. 0 also has a multiplicity of an even number. And then my +4 has a multiplicity of 1. So that's the only one that it actually goes through and does more than just touching it. Okay, so I just typed this in on my graphing calculator here. And then when I look at my graph, we'll wait for it. It's really hard to see because it looks like it's just so big, but you can kind of see where it hits there at the -1 that we said it would. Hits at the 0, but you can't really tell because this is really a crazy graph. So we really don't actually look at a whole lot of graphs like this, but this is a good enough basic graph if I asked you to graph it. Okay, the next example that I want you to do has to do with the example on page 305, and you're given the equation, and it is 0.5 t to the 4th. Instead of t, we actually use x's, so I need to actually write it in my y equals. So I have 0.5 x to the 4th, and mine might look a little bit different than yours. It's okay, plus 3.45 x to the 3rd, and then get out of your square root thing, minus 96.65 t squared plus 347.7 t. And then what you can do, you can look at a graph of that. It's not actually going to show up on the graph really. I can go into my table, so second graph, and I can compute all of these different things. Okay, and I accidentally didn't type in plus, I typed in times, and I actually wanted a minus sign instead of that. So now let's look at our table of values, and that will make a little bit more sense. Maybe not if I can't type anything in right. Okay, well I just figured out I forgot to push the X button. So in order to insert something on your calculator, you can push the second button and delete, so it says INS, and that is your insert button. So second, doing that, and then hopefully my table of values should work. And that makes more sense. That is what I actually wanted. So when I have 0, my y value is 0. So you guys can go through and you can use this to find your table of values. There's no reason at this point you really need to be doing things by hand. At this point, I've assumed you can do order of operations already, which is what all that the 4th and the 3rd and all those are doing. Okay, however, if I asked you what happened at half of a minute or half of whatever time frame I'm looking at, I can't use my 0, 1, 2, 3, 4, 5, 6. I need to go and I need to change what's called my table set. So I'm in my table, so think table, table set. So I'm going to push second window. The window is for my graph, the table set's for my table. Instead of going up by 1s, I'm going to go up by 0.5s. So if I asked you what happened at half a minute, I still don't want to look at my graph. Oh, let's see if it'll do it. So now what happened at half a minute, I should have 150.15. Your calculator will round whatever it's telling you to round at. If you are asked to do something in hundredths or thousandths, and it's only giving you like 0.26 and you want it to go out further, you should be able to change your mode. So here's just a bunch of things about your calculator. If I want it to go out to my fourth decimal place, or third since I'm on third, fourth. Okay, so now I'm going to go back to my table. And so it tells me 0.0000. It went out 4 decimal places. So these ones, it only leaves room, I guess, for certain amounts of things, but it will still like round as good as it can for that. It'll do as much as will fit on there. Make sure you read the problem really well, because a lot of your problems will say the number of years since whatever it is. So your equation is actually written with your number of years that you started with, or whatever your initial year was, that was your starting year. So make sure you actually plug in the right value for your variable that you're looking for the right value. Also, you can always do on your TI, if I go into my graph. So if I'm looking for how much whatever this equation represents, in this case it was ibuprofen, how much ibuprofen is in your system after a while, and I want to find out how much ibuprofen is in my system. In this case, since it's hours, if I wanted to know what happened since at maybe 5.5 or 6 hours, I can always go and look at my table, which we were already looking at here. But if I wanted to look at it, I can go into my graph, which I'm already at, and I can use my second calculate button. So second trace, so it says calc on the top, and I can figure out my value at a certain time. So maybe if I want 2.75 hours, so 2 hours and 45 minutes. Okay, and it will spit out my value. So I will have 325 milligrams of this medicine left after that much time. And it tells you what your time is in, and it tells you what your Y is in as well. So make sure you're paying attention to that, and you can tell me the units on your things as well. Right now I want you to do homework, or I guess tomorrow. I want you to do homework on page 306 to 309, and I want you to do numbers 3 through 66 by 3s.